Hello guys, the topic of our video is finding the cycle in the graph. Make yourself comfortable in this beautiful place and let's go. Okay, today we're finding the cycle in the graph and we will use it, we will do this using the disjoint set data structure which we already implement in the previous video. Also, I will take some previously defined data types, which was defined in our video about graph intro. So how can they basically work with the graph? If you don't see it, please see it. I will put link in the description. But it is very simple. Here we have some edge representation as a pair. And here we have instance of equality of the edges, but actually I think we don't need it here, but I will state. And we have the graph data type, which actually represent the list of edges. So edges of these types. So the graph is just a list of edges. So here we have we can see that we have created some graph G, and it consists of 4 edges from A to B, B to C, C to D, and D to B. And we have vertices function that receive a graph on input and produce a list of all the vertices of this graph on the output. Okay, and we have this disjoint set type class which implements the abstract data type. Here we have some instance for it, and now we can implement our detection cycle function very easily. So at first let's start with the type signature. Our function, I will call it haskell, and it takes some graph of type A on input and produce to us the boolean value. Okay, and I think we need ordering constraint here for the nodes of our graph. Okay, let's go to implementation. We have only one value of the graph here, only one argument, and I will pattern match it to have the access to its internal lists, which contain the list of edges. Okay, and here we need to define our function. So how I will detect the cycle. At first we take all the vertices of our graph and create the disjoint set from all the vertices. So we all at the first point they all just vertices, not connected with each other. It's just a separate points of the graph, and they defined in our disjoint set data structure. When they take the list of the list of the edges of this graph and start to do the union operation of our disjoint set data structure. So we have this disjoint set data structure which allows to us to make a set for some vertex. So at the first step we take all the vertices of a graph and make these sets. And then they take the list of all the edges and do the union for every vertex of the edge. Okay, and during this iteration process, we actually constructing our connection components. And at some edge, if the cycle exists, then at some edge we can do the connection of two components because there is a cycle here. And this fact is defined by this Boolean value. So if at some point it returns to us the false, this means that we have a cycle, and we can define our function in this way by this fact. And otherwise, if we go through all the ages and not find any cycle, so not found any false value here, this say to us that there is no cycle in the graph. Okay, this is the main idea, and we now can start to implement this iteration process. So I need some helper iteration function. I will call it go. It take two arguments. It take the list of the edges of the graph, and it take the disjoint set data structure. And here we need to define these names. So how can we get the list of all the ages? So we have so actually we extract the list here, and actually we don't need to define it. So we use it here, and one thing I need to define is our disjoint set. And our disjoint set, initial disjoint set, can be defined by extracting all the vertices of the graph. So we have vertices function, we provide the graph for it, and it's defined to us the list of all vertices of this graph. And also we have this helper function which built from the list of the vertices the disjoint set data structure for us, and we can use these two functions. And of course the type of this expression will be disjoint set of type A. Okay, we define our initial disjoint set data structure with separate vertices. Now I want to define the type of our helper function, and it's take a list of ages of type A, and also it take disjoint set data structure of type A and produce a Boolean value. Okay. And from here we can start from simple case. What if we have the empty list in our graph of age? In this case, no matter what is the disjoint set data structure, if they have no list of age, this means to us that there is no connection, and we can say that there is no cycle in this graph. Okay. But what if we have some list of ages here, and here we can unpattern match our list. We can extract one age from it, and this age also can be unpattern match because our age is created via this data constructor, and let's use it to unpattern match this age. And now I can unpattern match the vertices of the age to A and B. Okay, now I have the names for them, and of course I will receive a disjoint set data structure on input. And here I need to define the body of my go function. And here what we can do in this point, when we have these two vertices A and B, we can try to connect them. Connect the connection components to which way belongs. And if we will receive the answer that we do the connection, this means that there is no cycle and we can continue. But otherwise, if there is a loop, if we can do the connection, this say to us that we can stop. Okay, this leads us to implementation. So I use some guards here, and I need some condition which show me that there is no loop. If there is no loop, this means that I can go continue my iteration process with the tail of the list of the edges and some new disjoint set data structure where the these A and B components connected. But otherwise, what if there is no what if there is loop detected? So in this case, they can say that yes, there is a loop in this cycle, and they defined our function in that way. And here I need to define the no loop and this new disjoint set. Okay, and I think this can be done very easily with our union function. So our union function, let's look at it. So it has such a type signature. We need to provide the two vertices and disjoint set, and maybe we will receive the new disjoint set with the fact that was connection or not. But in our case, we will always receive the just value, because the we assume that we use in our graph, but actually I don't need any assume here, because actually our vertices built from this list, and this means that if vertices present in our list, this provide us this leads us that this vertices present in some of the edges. So the other situations is not possible here, and that's why I can use my union function and can extract from just from it without losing totality. Okay, but actually the totality broken, but fail of the function from just never happened. So let's use this union function here. We provide A and B to it, and we also need to provide the disjoint set. Okay, then we have this. We need to extract from just, and after that we need to unpattern match all the results. And the result is the first fact that we have no loop. Okay, if the connection was done, this means that there is no loop. Okay, and here we extract the new disjoint set data structure. Okay, and then we use this disjoint set to go deep to our iteration process. Also, I think we can try to compile this. So let's load our file. And we have some problems here. So I think I need to add for all here, for all A. And now it's done. We'll load our file. It's compiled. And now I can check the cycles. We have some graph here from A to B, from B to C, from C to D and from D to B, and it has the cycle. Let's remove this H from here, and we broke the cycle. Now it has no cycle. Now let's try to reload and check has cycle or not. You can see that there is no cycle, because there is no cycle in this graph. And what if I have this graph with no H's? Let's check this case also. Oh, there is no cycle. What if I have the graph only there is the one H? Let's check this. There is no cycle in this way. And I can, for example, add some new H here which go to cycle. What if I want to go from D to A here, and this we have somehow a square, and it has a cycle. So let's reload and check. Yes, you can see that we detect the cycle with our function. Okay, and also if I put the D to B, it also has a cycle. But what if I put the D to some A, B, C, D, E, some E? This tells us that there is no cycle. But what if I put A again here? We have a cycle. So guys, we detect cycle as this function. And I think that's all for today. Thank you for watching. Push like button, push subscribe button, and see you in the next videos, in the next meditation session. Bye bye.